Hello, my name is Timothy Hamilton, and today we're going to talk about molecular orbital theory, particularly the application of this theory to question 8 on the midterm. So, before we go into talking about the midterm itself, let's do a brief review of molecular orbital theory. So, molecular orbital theory is based on the fact that electrons have wave properties. And this means that they can interact with each other in bonds like waves. Such as when waves, for instance, when waves interact with each other, they form what's known as destructive or constructive interference. In terms of electrons, this means that when electrons interact in a destructive manner, they do not contribute to the strength of a bond, are thus called antibonding orbitals, which are designated by the sigma or pi sign with an asterisk, like so. However, if they do contribute to the stability of the bond, they are simply called bonding orbitals, which are signified by simply the sign of the type of orbital they're in. Now, it's important to note that molecular orbital diagrams are arranged from an increasing energy from lower to upper, much like regular molecular orbitals are. And it's also important to note that the increasing electronegativity goes from top to down, meaning the more electronegative element that's in the form of the bond will be lower and have thus its orbitals lower as well. Now the question number 8 itself doesn't actually deal with this itself, but it's still important to know it just in case. What it does ask, however, is bond order. Bond order is simply a reference to how strong the bond is, and in part is computed by simply taking half the difference between the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. Now, bond order is important because it's proportional to the bond strength and inversely proportional to bond length. Essentially, the greater the bond order, the greater the bond between the two atoms are, and most likely the shorter the bond length is. With that in mind, we can use bond order to predict which bonds are stronger based on the molecular orbitals that are located in the bonds. However, the molecular orbital diagrams are slightly different for different elements. For instance, for atoms with the lower number of atomic number of 8, they follow this diagram over here. And notice how the pi bonds on the pi bond of the 2p are on the same level, and thus when we fill it with electrons, they'll all occupy the same energy and thus be evenly distributed about. It should all be noticed that we only use valence electrons because these are the ones that are used in bonds. However, for elements of atomic number 8 and above, we follow this structure. Again, it's very similar to the above structure, with the only difference being here. It's also to note over here, in which case the sigma bond level has dropped 2 levels down. It's also important to note that the bonds themselves are generally antibonding, when antibondings have greater energy than their corresponding pi bond. And also that the bonds themselves have an average amount to equal 0, which is also based upon the wave-like properties. Alright, get specifically to question 8 on the midterm. The question asks to give the number of valence electrons, the electron configuration, and the bond order, and then to use the bond order to predict which has a stronger bond. So essentially, we need to know which of the pairs of elements has the greater bond order. And to do that, we need to make the shorter version of the molecular orbital diagram. Now, we do not need to actually put in the actual orbitals on the side, but we can still fill it up with use of the valence electrons. For instance, C2 has 8 electrons because carbon has 4 valence electrons, and thus 2 of these as 1. Now, this would fill up the molecular orbital theory which is in the molecular orbital diagram, which is this format because carbon has an atomic number of 6, which is less than 8 in this matter. So because we have 8 valence electrons, we start from the lowest to highest like any other off-ball principle. In this case, 1, 2, 3, 4, and then use Hund's rule, 5, 6, 7, 8. So now we have all 8 of the valence electrons filled in, and now in the correct orbitals. Now we can write the valence electron configurations. In this case, all we need to do is just write down which orbitals they fill in. So in this case, it would be sigma 2s 2 because of this over there. Sigma star, the antibody orbital, 2s squared, pi px, 2px squared, and pi 2py squared. Now we can figure out the bond order. So the bond order is basically 1/2 the difference between the electrons in bonding and antibonding. So in this case, we have 1, 2, 3, 4, 5, 6 electrons in bonding orbitals, while only 2 in antibonding orbitals. So this would be the bond order would be 1/2 of 6 minus 2, which would be equal to 2. Now, C2 plus, because of the plus side over here, would have one valence electron, hence the 7e minus, when compared to the 8e minus of carbon. So as a result, the electron orbital theory would look essentially the same, minus this last valence electron, because based on the off-ball principle, we would be the last electron to be added is the one with the most energy, and thus is the one that can be the most easily removed. Now, essentially, the electron configuration, the molecular is the same as above, except with the last term of pi py being only 1. So again, sigma 2s sigma star 2s both squared pi 2px squared for the 2 and pi 2py 1. Again, the total is also 8 electrons here and 7 electrons there. Now the bond order for C2 plus would be, again, the same thing. 1/2 minus the difference between the electrons in bonding minus the electrons in antibonding. In this case, it will be 1/2 minus 2, 4, 5 minus 2, which would be 1.5. Now, out of these two, C2 has a greater bonding order because 2 is greater than 1.5, and because bonding order is directly proportional to length, then it would be, therefore, it would be allowed to have, then we can determine that C2 is a stronger bond. We use the same process for the compounds O2 and O2 plus. In this case, we determined the first of valence electrons. Again, oxygen has 6 valence electrons in its atomic form, so 2 oxygens would have thus 12 valence electrons. Now, because oxygen has the atomic number, because that is an atomic number of 8, which is greater than or equal to 8, it would follow this pattern, which once again differs from the previous pattern we used. So we could first so now we know the valence electrons, we can figure out the electron configuration by simply following in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now, all we need to do then is now write this out in words to form the electron configuration. So, sigma 2s squared, sigma star 2s squared, pi 2px, actually we should follow by complete energy level, good catch. So pi 2pz squared, sigma 2pz squared, pi 2px squared, pi 2py squared, pi star 2px 1, and pi star 2py 1. So 2, 4, 6, 8, 10, 11, 12. Now we can calculate the bond order. So the bond order again is 1/2 times the difference between bonding minus antibonding, which in this case is equal to 1/2 times 2, 4, 6, 8. So it would be 8 minus 4, which would then be equal to 2. Now O2 again follows the exact same pattern of molecular orbital as O2 plus, but because of the plus over here, would have one less electron, hence the 11 valence electrons. So in this case, the pattern would just be the one less remaining over here. And again, we simply write the exact same valence above for the electron configuration. So sigma 2s, 2 sigma star, 2s, 2 sigma 2pz, 2 pi 2px, 2 pi 2py, 2, 2, 4, and then pi 2px 1. Now, again, all we need to do is calculate the bonding order, and again, we have 2, 4, 6, 8 electrons in bonding positions, while instead of the 4 previously in the antibody, we have 2, 3 as well. Which is 2.5. Now, 2.5 is greater than 2, and as we said before, bonding order is proportional to bond strength, which therefore gives us the answer that O2 has the greater bond strength out of this pair. So there you have it, an application of molecular orbital theory which uses molecular orbital theory in a question that asks about allows us to determine bond order and therefore bond strength.